Okay, so we're going to look at differential equations today. So let's just go ahead and get started. So a differential equation or sometimes I'll abbreviate it by DE. It doesn't really happen too often, but is any equation involving one or more derivatives. So these equations have a lot more things in them. So in algebra, typically your equations just have numbers and variables. So for differential equations, now we have numbers, variables, functions, and derivatives of functions. And with these, the solution won't be a number. In algebra, the solution to equation is typically a number, but the solution to a differential equation is a function. And if you, in practice, you're going to basically be solving for classes of functions, right? Your solutions are only going to be unique up to a constant, similarly to when we find antiderivatives. But if you have a specific value that you know the function passes through, which is known as an initial value, you can actually solve for a specific function. So to solve for a specific function, an initial value for the function must be given. So if we're given a differential equation and an initial condition, this is known as an initial value problem, or an IVP. So we do have some notational conventions as well. A lot of times we won't write using the full function notation. We'll just use letters to represent functions. Just it makes them look a little bit cleaner. So when we write DEs, often we'll omit the input variable in the notation. It's sort of just understood. So for instance, we would write y prime equals t times y, rather than y prime of t equals t times y of t. So we just sort of understand that y and y primes are functions of t. So, and then one last thing, we're not looking at all differential equations. Differential equations is a large branch of math that you can study in graduate school. You can look at ordinary differential equations versus partial differential equations and look at them in different abstract spaces. But we're just looking at a very particular subset of differential equations known as separable differential equations. So we restrict ourselves to the study of separable differential equations. So a separable differential equation is one that may be factored as a function of x times a function of y. Or any two variables that may be separated in that manner. It doesn't have to be x and y, but typically that's what we're going to be seeing. So that is maybe written something like dy over dx equals some function, say g of x, a function of x times a function of y, f of y. Something like this. Okay, so we've certainly had plenty of notation and definitions to start today. So let's actually look at some examples about how this would go. So let's say solve dy over dx equals x squared over y squared. So basically what you do here is you just kind of cross multiply on this one. So we treat kind of the differentials as if they're numbers. So we're kind of abusing notation a bit there, but everything works out. You'd have to take a class in analysis to really talk about the finer points of why we're able to do this. But let's just imagine you can cross multiply. Then we would end up with y squared times dy equals x squared times dx. And then basically what you can do is you can just integrate both sides to solve. So then the integrals are both very easy. With respect to y, this would be y cubed over 3. And with respect to x, this would be x cubed over 3. And then we would just have plus a constant because we don't actually have a specific point that that curve goes through. Now, for many of these differential equations, we have them as just curves. So I'll just stop once, there's no more differentials left. Although some of the homework problems, when we look at those on Friday, may require that you actually solve for y. So we'll do more of that. If you had to solve for y, basically you'd multiply everything by 3 and then take the cube root. But today I'm just going to focus on actually doing the getting rid of the differentials. So let's continue looking at some more examples. And again, we're just going to solve each dE. So again, the key is to just kind of separate variables the way we did in the previous problem. So let's say for this one we have dy over dx is equal to x times e to the negative y. So it might help to think of this as dy over dx. Remember, e to the negative y would be the same thing as divided by e to the y using the exponent notation. And then again, you can sort of cross multiply here, and you'll see you'll get e to the y times dy is equal to x times dx. So we only have things involving x on the right and things involving y on the left, and we can integrate. And then it's a very simple antiderivative. The antiderivative of e to the y is just e to the y. X has antiderivative x squared over 2, and then plus a general constant. So that's it for part A here. Let's look at part B. Let's say we have Let's use one maybe using the prime notation, y squared plus xy squared. Let's say it's multiplied by y prime, and let's say this is equal to 1. Anytime you're using the prime notation, I typically like to use Leibniz notation, just dy over dx instead, because it helps me see how my variables are being separated. So I would start here and just say, okay, well, this is y squared plus xy squared times dy over dx, and this is equal to 1. And then how do you actually separate variables here? Well, you're able to factor out a y squared from that set of parentheses. So if you factor out a y squared, you'll end up with 1 plus x, and then you can pull that y squared out, and then we have our dy over dx. So to move the dx to the right, we would multiply by dx, and then the 1 plus x we would want to divide by. So on the left, I'll just be left with y squared dy, and on the right, I'll have 1 over 1 plus x times dx. So now my variables are separated and I can integrate. And we end up with y cubed over 3, just using the power rule there. And then the right-hand side, we have the natural log of the absolute value of 1 plus x plus a constant. Technically you might say, oh, there's a u substitution there, but the point is you would let u equal 1 plus x, and then du is just equal to dx. So there's not anything additional coming out of that u substitution that you have to worry about. Okay, so now let's look at some initial value problems and see how those differ. So an initial value problem, the first step is to solve the DE as usual. Then the second step is essentially to plug in your point and figure out what that capital C is, what that specific constant is, and the initial value allows you to do that. So we want to solve each IVP. So this first one will say we have dy over dx is equal to x squared y, and our initial condition is y of 3 is equal to 2. So again, separate your variables. So divide by y to move that to the left. So we end up with 1 over y equals dy, and then just multiply by your dx, and you have x squared times dx. So your variables are separated, and you're able to integrate. Again, usually with these, you're just multiplying or dividing to get the y's to the left and the x's to the right. That's all I'm doing for that first step. And then the antiderivative is pretty easy. 1 over y has antiderivative natural log absolute value of y, and x squared is just x cubed over 3, and then we have plus our constant. So now's the part where we're going to plug in that point. We're going to use that y of 3 equals 2. That means if I plug in 3 for x, I get 2 for y. So that means the natural log of 2 is equal to 3 to the third power over 3 plus a constant. So we can figure out exactly what our constant is. So we end up with the natural log of 2 equals 9 plus c. So the natural log of 2 minus 9 is our value for c. So we could replace that back in this original equation. So essentially, I'm just going to plug this back in up here. So my solution, my exact function would be the natural log of the absolute value of y is equal to x cubed over 3 plus the natural log of 2 minus 9. So that is the solution to this particular IVP. So we were able to not only figure out the family of functions, but we could also figure out the exact value of c because we knew that one point that the problem actually went through. So essentially, there's just one more step after solving the DE for each IVP. Okay, let's go ahead and look at another initial value problem. I think I can fit this on the same page. So let's say B. We have dy over dx is equal to e to the 2x over y squared, and the point it passes through, y of 0 is equal to 3. So again, we want to separate our variables. So multiply by y squared, we end up with y squared dy. And on the other side, we have e to the 2x dx. And then we can integrate. So we have y to the third power over 3. And for e to the 2x, remember e to the kx has antiderivative e to the kx over k. So this will just be e to the 2x over 2 plus a constant. And then we just plug in 0 for x and 3 for y. That's the point we have here. So again, we're getting 3 cubed over 3, which is just 9, equals e to the 0 over 2, which is just a half. So essentially 9 equals 1/2 plus c. So when you subtract, you get 17 over 2 is your value for c. So we have, again, we're just plugging this back right in here since we found for c. So our solution here is y cubed over 3 equals e to the 2x over 2 plus 17 over 2. Okay, so let me give you guys one to try. See if you're able to do it. A little bit trickier. So example, we'll say try at home. So this one we have x squared plus 1 times dy over dx, and this is equal to xy. So go ahead and give that a try. I will say that this one does involve a u substitution, but it's not a difficult u substitution. So let me give you a few minutes to try that. Okay, so hopefully you've had a chance to give this one a try. So when we're separating, we basically have to divide by y to move that to the left. So we're going to get 1 over y dy on the left. And then the x stays on the right. We multiply by the dx, and we have to divide by x squared plus 1. So we have x over x squared plus 1 dx. So this is what we're integrating. So we end up with the natural log of the absolute value of y on the left. And on the right, we have to do a u substitution, right? If we're going to do that integral, let's just go through the u substitution. We would let u be x squared plus 1. So du would be 2x dx. So 1 over 2x times du would be dx. So, I wrote dy. That should be du. I thought I switched. So then when you replace your integral, you get the integral of 1 over 2x times x over u du. So you get 1/2 the integral of 1 over u du, which is just going to be 1/2 natural log the absolute value of u plus a constant. So u was this x squared plus 1. So my antiderivative here is 1/2 natural log absolute value of x squared plus 1 plus a constant. So that was the u substitution. So this is the u sub for the right-hand side. All right, let's look at a couple more examples. Let's solve another initial value problem. And again, on this homework that's due Friday, the last 5 questions are all differential equations and IVPs. So we'll get some more practice on Friday. And if you get stuck, just let me know and we'll answer any questions you might have. So let's say we have dy over dx is x over y. It's a pretty easy dE to solve. And let's say y of 0 is -3. So this one's very straightforward. We end up with just y dy equals x dx. So when we integrate, we simply have y squared over 2 is x squared over 2 plus a constant. And then we're plugging in 0 for x and -3 for y. So -3 squared over 2 equals 0 squared over 2, which is just 0, plus a constant. So 4.5 is our value for c here. So again, that's just y squared over 2 equals x squared over 2 plus our 4.5. Or 9 over 2 if you'd rather just use fractions for everything. So did have one more from WebEx. Let's have a look. I was looking at number 28 from 6.4 for one last example. Why did it do that? Okay, there we go. I just wanted to copy the exercise because I didn't know if it was, I didn't have it written in my notes. Oh, the very last one on the previous page. So let's have a look at this one maybe. So maybe I can use the snipping tool. Okay, so we'll save this. We'll save it in the 1045 folder though. So let's say D E. Okay. So let's look at this example. So this is a word problem, but it, there's not a lot to turn it into a equation here. So insert picture. So here we go. A little bit bigger. Okay, so we have a radioactive material that's decaying at a rate equal to 1/5,000 of the amount of the material present in grams per year. An experiment starts with 20 grams of the material. So that's going to be the initial value. Basically, at time 0, we have a mass of 20 grams. So we want to write a differential equation that describes the situation and solve it to find a function that gives the amount of material present after t years. So we already are kind of familiar with this type of problem. It reminds us of half-life problems, so we know essentially the answer is going to be some version of an exponential. But we can actually do this in the guise of differential equations as well. So let's say if y equals y of t is the amount present after t years, basically what we can have is we have dy over dt is 1/5,000 times y. And we know our initial amount we said was y of 0 is equal to 20, right? So think about that. It decays at a rate equal to 1/5,000. So dy over dt is representing a rate. That's what derivatives do. And it's 1/5,000 times the amount that was present, which is y. That's exactly how we defined our function. So very naturally, this problem can be written as a differential equation. And then it doesn't take too much work to solve it, right? We move the y to the left, so we get 1/y dy. And we can say, okay, this is just 1/5,000 dt. And then integrate both sides. So we have the natural log of the absolute value of y was equal to 1/5,000 times t plus a constant. And then if you plug in 0 for t, you'll get 20 for y. So the natural log of 20 is equal to 1/5,000 times 0. So that goes away. So essentially we get the natural log of 20 equals c. And that's actually pretty close. I mean, to 2 decimal places, that's 3.00. So our solution here is the natural log of the absolute value of y is equal to 1/5,000 t plus 3. And you'll notice actually, as we were speaking about it, we said, well, we've got like a half-life type of situation, so we know that our a function should be something like an exponential. If you think about this equation here, the natural log of, say, the absolute value of y equals 1/5,000 t plus 3. Technically, it was the natural log of 20. But basically, you can exponentiate both sides with base e and realize this as an exponential function. So on the left-hand side, we get y, and on the right, basically we get e cubed, or e to the natural log of 20 times e to the t over 5,000, which essentially gives us 20 times e to the t over 5,000, right? Which we should have been able to do just from exponential equations, right? We know that the function would have an initial amount of 20, and then since it's 1/5000th present, that's what's giving the constant in the exponent there. So that's just showing the connection from the actual result we get for differential equations, and if we would explicitly solve for y, how it would give exactly the exponential function we would expect to see. So are there any questions here? Okay, if not, then I think that will do it for today. So I'll go ahead and stop the recording.